If you don't know me, I am a control automation engineer. I have a PhD in systems and control. Since 2013, I'm with the Space System Divisions of the National Institute for Space Research, INPE, in Brazil, where I am the mission architect and also the technical lead of the Attitude and Object Control Subsystem, or AOCS, of the satellite Amazonia 1. In Julia community, I'm also the developer of some packages like Satellite to Box, reference frame rotations, pre-tables, terminal pages, and some others. This is a little bit different presentation because I'm not here to speak, to talk about a package or an algorithm or something. I'm here to show how we are using Julia to solve a problem, which is how to develop attitude control subsystems for satellites. This is what I'm planning. I'm going to talk what we did until so far and what we plan to do next. But first, let's talk about Amazonia 1. What is Amazonia 1? Amazonia 1 was the first remote sensing satellite fully integrated and designed in Brazil. This was the project that started it all. It was launched successfully on February 28, February 2021, 2 years ago. And Julia was a key technology during the AOCS development. Here is a picture during the, oh, my mouse, where is? No, that is a picture of the satellite during some tests, and my last picture with it in India before the launch. But before starting, let's talk about what is attitude control. Attitude is not altitude, I did not misspell this word. It's just the orientation of an object in space. So if I take my cell phone and move it like it, I'm changing its attitude. This is attitude. So what is attitude control? For this, I'd like to show a real footage. This was obtained during the injection process of the Amazonia 1. The satellite is exiting the launcher, and it starts to do the things, open the solar panels, and then you see it's changing its orientation to point the solar panels towards the sun. This is attitude control. I'm changing the orientation of the satellite to accomplish some tasks. But why do I need to do that? Mostly of satellites have some payload, and you have to point this payload towards something to acquire your data. For example, Hubble needs to point the lenses to, I don't know, a star or something to get this image. But how do I do this? How can I control the attitude of satellite? The first thing you need to do is to measure the attitude. You have to measure it. And for this, you have many sensors, some sensors, magnetometers, star trackers, gyros, and so on. And also, you have to change the attitude. So you need actuators, like reaction wheels, magnetic torque rods, and thrusters. Well, this was attitude control 101. But now let's see how we develop attitude control and how Julia is helping us to do so. First of all, you might imagine that it is almost impossible to replicate on ground the space dynamics for a rigid body. You cannot try to, for example, levitate the satellite and remove all the perturbations so that you have the same dynamics. It's impossible. There are some academic works trying to achieve that, but it's very difficult to, I don't know, levitate a 700 kilo satellite. So simulations are essential. We need simulations from the design phase up to acceptance stages. And the results of those simulations are what we use to do the go. The system is okay, we can launch. For example, this is a laboratory in Brazil. Inside that chamber, we have Amazonia 1. In one of the final tests, we are doing some kind of thermal cycling in vacuum. And if you look, I cannot move my mouse, but if you, sorry, the live footage, I'm just step out. If you look here, you can see many computers. Those computers are simulating the environment. Those computers are simulating the sensors and sending those messages to satellite that it's working just like it will be on orbit. So we have a satellite in the loop simulation here. And this is what we use to validate the system. Okay, but given that, sorry. Given that we need a validated simulator, we decided inside this project to create one simulator to test many things. Amazonia 1 was the first mission that was built on top of what we call the PMM, a Portuguese acronym for the Multi-Mission Platform. It's a platform that you can use for many missions. So we decided to develop this high-fidelity AOCS simulator to verify problematic scenarios. This was the project that led me to create reference frame rotations in Satellite Toolbox. And we used the differential equation from SciML ecosystem as the thing that glued everything together. This is a huge project. We are simulating each sensor I showed to you, each actuators, the warp dynamics, perturbations, and whatever. If we remove the differential equations, of course, we have 40,000 lines of code. It's a very big project. We use this inside this project to make a very big analysis for all the possible errors we could find during the launch. We simulated 35 billion minutes. We could do this because it is very fast. It's really fast. So we find problematic scenarios. We find situations that if it happens on orbit, we have to act very fast to save the missions. So we were very well prepared. How does it work? You have these continuous sets of variables, orbit propagation, sun position, magnetic field simulations. And then you have this it's very interesting thing called callbacks in the differential equations where you just stop the integration, run some things, and changes, which just happens to be exactly how the satellite works. Inside the satellite, we have a computer that works in defined steps and executes the things that it must execute. So this is what we did to simulate the systems. And just to show how it works, just a simple interface where you have the initial conditions, you can put any kind of variable you want there, and it executes. I'm doing here, I think, 12 hours of simulations in this laptop here, nothing fancy, in 15 seconds. So it's really very fast. It's really very fast. And we are propagating orbit, computing perturbations. But I don't need just to be fast. It must be accurate. And we use Amazonia 1 to validate the simulator because we need, at INPE, we need to validate the simulator for the future missions. In this case, we obtained the very first telemetry frame from the satellite. So the satellite was launched and communicates with the ground. We take the very first telemetry frame, obtain the initial state, and input to the simulator. On that figure, the orange curve is what the simulator said. Oh, Amazonia 1 will do this. And the blue curve is what the Amazonia 1 really did. It is the total angular momentum on the reaction wheel set. There is a lot of curves besides that. You can see the match is almost perfect. We cannot have a perfect match because the initial state was obtained from sensors and the sensor has errors, but it's a very good one. So we can say that the simulator is validated by looking this picture. But we went further. When you assemble a sensor or something on the satellite, you always have errors. You cannot assemble a gyro or a Star Trek perfectly. It will have misalignments, for example. For some missions, and Amazonia 1 is one of this, we must calibrate those sensors on orbit. We have to realign and change some internal properties in the software. So we use the same simulator to validate the algorithms that we apply to calibrate the Amazonia 1 sensors of the attitude and orbit control subsystems. When everything was done, we start to getting those kind of pictures. This is from South Florida. You can see this is a very sharp image. We can see roads, we can see a boat up there, all those structures. The only way to obtain a figure is so sharp is if everything is working. And the attitude and orbit control subsystems is one of those parts. It's more or less like this. If I try to take a picture of you shaking my hand, it will be blurry. The same thing happens up there, but it's much harder because the subject is 700 kilometers away. So, given this picture, given the results I show, we now we are confident to say that our simulator are 100% validated. But then we reach what I call the N simulator problem. To develop the AOCS, you have to go through many steps. I list just some of them here. For example, when we are designing the control loop gains, I need to have a simple rigid body simulator and a simple reaction wheel simulator to design my control gains. If I want to design the attitude estimator, I have also to implement some kind of rigid body simulator, and I have to simulate all the sensors. If I want to design the orbit estimator, of course, I have to code some orbit simulator and also the GPS simulator. If I want to turn the reaction wheels, I need the reaction wheel simulator. And when I'm testing the entire system, as I showed in that picture, I have to, I must implement a full simulator. Do you realize how many times I said the word simulator here? So this is the N simulator problem. At each phase, one engineer codes a simulator to solve the problem. And normally it's even in different languages. For example, the control engineer likes MATLAB very much, more than I want. And so the code is in MATLAB. We cannot just take it through the other phase until the implementation in C++. And the biggest problem here is that we don't have means to perform a test phase by phase, because the result of one phase cannot be just compared to the next one, because the assumptions in the simulator are different. So this is a big problem. How do you solve today? We wait for the last phase, where we have this hardware in the loop test with validator simulator. If something goes wrong, okay, let's redo the software. But it costs a lot. The simulator on that phase happens in real time. If we find some error in the software, we have to go back, emit a new version of software, and go to pass the entire validation campaign again to test for regressions. So it costs a lot. Hence, INPE in Brazil, it's the National Institute for Space Research. We are a research institute, so we are always looking how to improve things. And now that Amazon is working well, we are trying to see what we can fix, what we can improve in terms of the AOCS. And today I'm going to talk about how this N simulator problem is being solved. Okay, this is the previous picture, how the simulator works today. By looking at that picture, I was staring at that, and I see, well, this is the computer digital logic. All the algorithm, all the AOCS happens there. The continuous variables are things that does not change. The geomagnetic field does not change if you change your mission. The orbit propagation does not change if you change your mission. So, if we remove this and design a good interface using the same callback structure of differential equations, we can, for example, plug a high-level software written in Julia to control the satellite attitude. We can plug the embedded software, the C++ software that we run on the satellite. We can plug the processor simulator. Processor here is the satellite onboard processor, which is completely different from what we have here. We can even plug the hardware in the loop simulator with the satellite assembled. How this, I'll try to show in a very simple way how does it works. The first thing you have to do is to update the dynamics. Do one step in the ODE. Then you create some kind of sensor messages that complies with the interface we developed. From the other side, we have the AOC software, the attitude and orbit control software, which can be everything, anything. We can have the entire satellite AOC software, or we can have just one small function to test one part. But it must decode the sensor message to obtain the state of the satellite. It iterates the control algorithm, do whatever it needs to do. It then creates the actuator message, complying with that interface. And then the simulator decodes those actuator messages, update the states of the actuators, and propagates the loop, and the things goes on forever. Given this kind of interface and design, we developed a 4-stage process to create algorithms for the attitude and orbit control for the satellite. On the very first stage, we have algorithms developed entirely in Julia. So you have, for example, the sun determination algorithm, part of it. It's written 100% in Julia. This is the stage where Julia really shines, because if we are coding in other language, say, for example, Python, this stage will be very slow, because the entire software will be written in Python, not in C++. In Python, if you don't translate to C++, it usually is slow. In Julia, we can have the entire, and we have now, the entire embedded software code in Julia with excellent, with very fast speed. So in this first stage, we can do Monte Carlo simulations. We can obtain a lot of test results to validate the other stages. And we, of course, since Julia is dynamic, a dynamic language, it's very easy to debug, it's very easy to change things. And we spend some time on this process. When we are happy, oh, this is a good algorithm. To test this algorithm, we have to, for example, I select some kinds of initial states, and those initial states provide this kind of results. These are the test results we need to see on the other stages. And then I take this Julia code and pass to a programmer. We translate it to C++. And using this amazing package called CXX-wrap, we can integrate the code following that interface with the Julia simulator. But what is very interesting here is that this code is the same code that the satellite computer runs, without changing a single call. So here we can test, again, with Monte Carlo simulations, looking all those initial states, and see if the results are correct. We can spot bugs and whatever, with the very same software we will use in the embedded computer. In the third stage, we went a little bit further. We take the software and execute it inside the processor simulator, because here we can analyze if the memory consumption is okay. We have a very limited memory inside computer for space applications. We can see if the computational burden is okay, and among other things. Up to this stage, all the development happens within the AOCS team, which is very important because nowadays the satellite normally has only one computer. And inside this computer you have everything. You have thermal control, you have data handling, you have the AOCS, and other. And people will not buy a lot of satellite computers for those teams to make the development. So it's important to reduce as much as possible the usage of this flight hardware. Using this process, we can reach the third stage where we have the final AOCS code without requiring any external computer or simulator of the real satellite computer. And also, up to this stage, all the simulations does not occur in real time. 1 second of simulation is not 1 second in real life. So we can execute very long simulations that last days, weeks, without problem. And in the last stage, we take this code, pass to the computer team, which integrates inside the satellite embedded operation system and executes a hardware-in-the-loop simulation. It is working right now. Here is our test laboratory in Brazil. On the right, you have the satellite computer connected through that hack to the simulation computers here. The three from the left to the right, no, sorry, from the right to the left. The three are just computers to interface with the satellite computer, and this one is the Julia, the same simulator I've just shown here, running, closing the loop of everything. What is very interesting here, very important, is that since all the phases shares the same simulator, it's very easy to compare the results because it must be the same. So all the errors can be spotted much earlier. Currently, we have 50% of this next generation AOCS software in C++, and we achieved this value with a huge gain in time. Nobody anticipated that it would be so fast to reach this point. And up to now, not a single error was identified during this final stage test here. All the errors were obtained on those 3 first stages. And when we run the simulation here, we always got it in the first time. So, sorry for the ugly picture. It's the only one I could show for you, but I will try to explain what it means. To the right, we have the first stage. We have the solution. This is a variable related to the reaction wheels. We have 4 reaction wheels, so 4 curves. So the first stage in the right is the result from that 100% Julia simulation that we obtained in the very beginning of the development. So we know that with a set of initial conditions, we must see this kind of result. The x-axis is time in seconds, so it is almost more than 8 hours. And in the left, we have the hardware in the loop simulation. The computer of the satellite is running the C++ code with the operational system of the satellite, with simulations, whatever, just like I showed before. And it's very easy to see that things is working because the one curve is just equal the other. We have better plots here, but when I plot using the same system of the right, the plot was just equal. I will show here, you'll say, oh, you were lying. You just copied the plot. But this is what we saw. And this is working. The problem here, suppose that we spot some error here, that the curve was completely different. Then we have to fix it and execute this test again. But on the 4th stage, things happen in real time. The satellite computer are executing real time. So this took 8 hours to obtain. And if we want to go again, it's another 8 hours. And it is just one test of the entire validation campaign. So costs a lot to fix errors in this last stage. That's why we are gaining so much time. Okay, so to wrap up, Julia language and its ecosystem are allowing us to build the next generation AOCS software with considerable gains in development time and cost. I think maybe you know now how we are solving the N simulator problem, because with that interface and that system, for example, the control engineer who likes MATLAB a lot can just go to that simulator, change the gains, and see how it works. He doesn't need anymore to develop a simple simulator or something. He can use the real stuff. Next step is to continue advancing this kind of integrations. Up to the instance, we have the entire satellite with a closed loop simulation using the same simulator, which will perform the final validation test before the launch of our next project. And in the future, I'm really trying to do this. I have some projects in mind. Maybe we can embed Julia code itself inside the satellite. If we can reach this point, then many of those stages will be gone because we will not need to translate Julia code to C++. So, conclusion. We are using Julia to solve the N simulator problem, and I really hope that Julia helped me to solve the 2 language problems in satellite engineering, which today we cannot solve. Okay, thank you very much. I'm open to questions. Okay, for the first questions, no, we don't have. This is the problem. That's why we must have a validated simulator. There's nothing else you can do. If you flip a sign here, you won't discover it up there. So no, we don't have any other additional method. And for the second question, if you look the results, there is things you want in Julia from the developer survey. I am one of the vote small binaries because this is required for this kind of task. We can avoid allocations. The entire software written in Julia does not allocate. We can avoid garbage collection. We can avoid everything, but we do not have small binaries yet. That's the problem. With small binary, we can embed the Linux system running this, and I think we will be fine. Okay.
Thank you. One of the slides, and I can just kind of describe it, you kind of described that this state of the actuators and the actuators themselves are in the simulation. Well, that works too. So the actuators are in the simulation. If you had a situation where you wanted to put your actuators in a hardware-in-the-loop simulation, how would you, that's one of the difficulties that we kind of had because we have kind of like a similar setup, and you have that message passing interface, but that part is like a fundamental part of your simulation. So how would you kind of handle that with this?
This is a very nice question. We have two modes. The first one is entirely simulated. Then, for example, the reaction wheel is simulated inside the simulator, and we are communicating. And we have a second version where the reaction wheel is plugged into the computer. The computer command the reaction wheel, read the state of the reaction wheel, and send to the simulator its states. Because, for example, for the dynamics, the system only needs to know the angular momentum in the reaction wheel. So if I get this from the computer telemetry, I can close the loop with the actuator in the loop or entirely simulate. We have these two modes. It's possible. But magnetic torque rod is not that interesting because it's just a current. So you send to both, to the simulator and to the actuator. But the reaction wheel is more a bit complicated, and we do this by reading the telemetry and feeding the simulator.